Hello everyone and welcome back to Mitchell's Physics Review. Today we're going to be working on equilibrium. So let's look at our question. A 9,200 Newton shark is supported by a rope attached to a 4.8 meter rod that can pivot at the base. Alright, let's look at our givens, which are pretty simple this time. We know that W, or Fg in this case, the force by the Earth acting on the shark, is 9,200 newtons, and we know the length of the rod is 4.8 meters. If we look a little closer at our diagram, we can also see our angles of 60 and 20 degrees. First up, before we go into anything mathematical, we need to look at this conceptually, and the best way we can do that is through a torque diagram. So, a torque diagram is doing all the forces acting on the system, and it's a little different than a free body force diagram, but if you practice, you got this. So, let's start at the hinge. We know there's going to be a normal force upward, or FV if you want to say a vertical force. We know that there's going to be a force to the right. Now, how do we know this? We know this is an equilibrium, guys. So when we look up at the top and we see that there is a component going to the left over here, we know that there has to be another component going in the right to balance forces. So we know that the hinge has to have a force going towards the right if we have a force going towards the left, or one of our components from the tension force. Next, we have our bar. Then we have Fg, or just W, the force or the weight of the shark, which is 9,200 right down here. Then we have the tension force at 20 degrees, and we know this line, the angle right under this horizontal component, is going to be 60 degrees. And then our vertical component will be right there. So we have a little quick look. Get used to this diagram. We're going to be traveling back here a lot for this problem, so be ready. Okay, everyone, let's look at part A. Calculate the tension in the cable between the rod and the wall, assuming the cable is holding the system in the position shown in the figure. Okay, so we're calculating the tension in the cable between the rod and the wall. So how are we going to do this? Well, we're going to start by looking at torques. So we know since the system is in equilibrium, the net torque should be equal to 0. And we know that a torque is a force that causes rotation. In this case, we have 4 forces in our system. However, if you look at our net torque diagram, barring all of the signs, all the lengths, just at the forces, Ft and W, you'll notice we only have 2. Now, why is that? Because when we're calculating the net torque, we do not use the forces from the hinge. So we're not going to use the Fn upwards, or the Fe if that's what you want to call it, or the Fh. So we don't use the horizontal or vertical component of the forces from the hinge. So now we're only looking at the weight times Ft. So let's take a look. Ft and W, we're going to have that. And why is it minus? Well, they're going to be in opposite directions. One is going up, one is going down. But we can also think of this as one is going to cause a counterclockwise rotation, and one is going to cause a clockwise rotation. So they're going to be opposite of each other. Now we have length over 2, because the center of mass of the system is in the middle of the bar. So we need to cut that length in half. We can't just use 4.8. Otherwise, we're not going to be getting the right answers, and it's not going to work. But you might be asking, now, why sine theta? Or why cosine theta? Well, when we are doing our distances, we're looking at L2, but we're also looking at the perpendicular distance to the force. So if this force is going down, the perpendicular distance is going to be here. If we're calculating the force going up here, the perpendicular distance is going to be this one right down here, that horizontal component. So that's why we're going to substitute in sine theta or cosine theta whenever, or to find the perpendicular distance. So in this case, it's going to be ft times L over 2 times sine of theta minus w times L over 2 times cosine of theta is equal to 0. Now we can say that we can move w times L2 times cosine theta over to make them equal to each other. We can cross out the L2s. And then, before plugging in any numbers, it's best to do this conceptually. We can find that ft is equal to w cosine of theta divided by sine of theta. Now from there, we can plug in all our values. We know what w is, we know cosine, and we know sine, and we know the angles. If you're confused about how to get the angles, remember, we're always using the angles to find the perpendicular side. So this one or this one. So whenever you're looking at that, that's how you're going to know what angle to use to find the perpendicular distance from the force. Once we solve for that, we get the tension force is equal to 4,671.04 newtons. Thank you. Okay, let's look at part 2. Find the horizontal force exerted on the base of the rod. So we know since it's a force exerted on the base of the rod, it's going to be from the hinge on the rod. But before we jump into this numerically, let's look at it conceptually to find the direction. So we know that Ft is made up of a vertical and horizontal component. We also know that that horizontal component is going to the left. Now, take a pause there. This system is in equilibrium. What does that mean? It means all the forces must equal to 0, which means they must be balanced. Okay, resume. Now, if we have a horizontal force pointing to the left, then we must need a horizontal force pointing to the right. And that is going to be the force from the hinge on the bar. So we know this is going to be pointing to the right. So we can answer this already. The direction should be to the right. So now we can look at the problem numerically. We know that the net force in the x direction should equal to 0 like previously stated. We could write this as FH minus FT cosine theta equals 0, calling right the positive direction, or we can just skip that step and write FH equals FT cosine theta. So, we know what FT is already, but why do we know it's cosine of 20 degrees? Because we're looking for the horizontal component. I can't reiterate it enough. We have to make sure we're looking for the same component. We can't be doing a horizontal and a vertical in this problem. That's not what we're looking for at this step. So, the cosine of 20 degrees will give us the horizontal component. From there, we can solve. We take 4,671.04 cosine of 20 degrees, and we get that the horizontal force by the hinge on the rod is equal to 4,389.34 newtons to the right. So, now, let's look at part C. Find the vertical force exerted on the base of the rod. Ignore the weight of the rod. Okay, let's take a look at this conceptually like before. Now we're looking at all the vertical forces or the vertical component of a force to find the Fn or Fv, whatever you want to call it, the vertical force exerted by the hinge on the rod. But how do we know which direction it's going to be? Well, if we even look at our picture, we know that the tension force should be less than the force of W of the shark hanging. So we know to make sure that the system is in equilibrium, we're going to need another net force to balance the forces in the y direction and make the net force in the y direction equal to 0. Now, let's look at this problem numerically. Like previously stated, we know the net force in the y direction must equal to 0. Now we're going to use Ft sine 20 degrees plus Fv equals W. So, y sine 20, like before, with the x direction, this time opposite. Instead of the horizontal component, we're looking for the vertical component, which would be the opposite, so it's going to be the sine of 20, not the cosine of 20. So then we can just rearrange our equation and we can find that the vertical force is equal to W minus Ft sine theta, which is 20 degrees. And then we can plug in W, we can plug in FT, we can plug in the angle to finally get that. The vertical force exerted by the hinge in the y direction is 7,602.41 newtons. Great. Now, to finish off this lab, I want to talk about some things that I struggled with that you might be struggling with too, and you don't have to feel as bad. Personally, when I first started this problem, drawing the torque diagram was really confusing to me. I kept forgetting that the forces from the hinge don't count in the torque, and it was just not great because I kept getting confused and adding too many forces into the net when trying to calculate the net torque, leading me to a wrong tension force. So, the one thing that I learned to remember and that you should keep in mind too, a key point of rotation is that when talking about torque, we don't include the forces that the hinge is creating or that by the hinge on some object. I hope you enjoyed this video. I hope it helped you like it helped me, and I hope it helped you gain a better understanding of rotation. Thank you.